iPad back up and running here. Okay. So the first thing I just want to point out is just that the homework this week is currently just due on Friday. We've gotten kind of in this, I ended up extending one a few weeks back. We've been in this Friday groove, and there's no hiding that we're not going to be ready for it till Friday. So I think maybe by next week we'll be able to get out of that groove because, I'm sorry, this is the test that's there. This Friday the homework's due. Sorry, I was originally talking about this. So we've got our homework due this Friday. And our next test is going to be next Friday. And so I think after that, we'll be able to get back into the Wednesday night homework thing. We just realized that that's what's going on. I posted a bunch of practice problems and stuff to Blackboard. And the stuff we're working on today will be on that test. And so I'd like to just jump right in. I'm happy to look at some homework problems or things like that, though, if people wanted to do that first. I don't have any homework or anything you want to look at? All right, if there's not, let me just open the chat up too so I can monitor that. Okay. If there's not, we were in the middle of introducing this concept of finding max and mins. And I mentioned on Friday, that's like one of the real big topics in calculus. And one of the most useful things is being able to figure out maxes and mins using the derivative, right? And so I took you through this picture, and I'll just kind of remind you of a few of the things. Let me highlight a few of the things. Oops. A few of the things we talked about. Just kind of, we talked about the idea between a global and local max, right? So the biggest one versus the one that's still a max, but it's not the biggest. And the same thing happens with mins. We've got local and global mins as well. And sort of the key thing, which I'll zoom in on this one peak, you can see the main information on this one peak, right? The main idea is that at the top, the derivative is 0. And so we find these critical points, these maxes and mins, by taking derivatives and setting them equal to 0. But when we end up finding them, we won't be able to tell right away whether it's a max or a min, right? All we know is the rate of change is 0, so it could be either. And so the thing we had pointed out was, well, hey, if it's a max, it's going to be increasing before the peak and decreasing after the peak. And so not only can we use the derivative to find the points, but we can plug points into the derivative to figure out whether or not it's a max or a min. And so that's what we're heading into right now. That's what today is going to be spent doing. And I just kind of re-summarize some of these things. And so the first thing we'll just note here is the way we find critical points are, number one, solving the derivative equal to 0. That's going to tell us the flat points, and so that's going to be the maxes or the mins. So let's make note of that. So this will tell us, tells us the flat points, quote unquote, right? The places where the rate of change is 0. And so these will be maxes or mins. Oops. Maxes, mins, or what we'll learn actually, the third type, or points of inflection. We may get to that today or definitely next time. And so the first thing we do is we take derivatives, set it equal to 0. That's how we're going to find these interesting points, quote unquote. And the second thing that's defined as a critical point are discontinuities. And so we find discontinuities just by looking at the function or the derivative and seeing where they don't exist. So number B, or part B here, is we see where the derivative or the function are undefined. Right, we look for places they do not exist. So kind of thinking back to the continuity section, it's just generally what we know about functions. We look for discontinuities by doing that. You know, the sort of the calculus part here is part A, right? Because we're taking derivatives and we're sort of evaluating the derivative in that sense. Part B, yeah, you're doing things with the derivative, or you're at least taking a derivative, but it's less of a calc topic and more of a just general good thing to know. All right, so that, you know, you can see the next couple pages are exploring this concept. So can I clarify something before we keep going? Yeah.
Oh.
You can say something?
Oh wait, was that just me echoing?
Was
I thought somebody else was talking. Jeez. What does that say at the start of B? Does it say C?
See where?
Oh, okay. Thank you.
Anything else? Okay, so what I alluded to a second ago was we take derivatives, we set it equal to 0. That's nice because we find flat places, quote unquote, but we need to figure out what kind of flat place is it? Because just kind of looking back up to this picture, right? Is it this kind of flat place? Is it a max? Is it this kind of flat place? Is it a min? Or we've seen this other flat place, which we haven't quite explored yet, the point of inflection. So let's talk about how we figure out which one of those three things it is. So that's what's being explained by the first derivative test. Right? This is something that comes up quite a bit in future homework problems, and we'll see it on the test. And just this is a good way to classify critical points. Okay, so the first derivative test, and we'll have a second derivative test as well. So it's a way, not the way, but a way to classify critical points. And let's do a couple pictures here to explain the idea. On the first picture, let's draw a max. So I'm going to draw a picture of a max that does this, right? And on the second picture, I'm going to draw a min. So it does this. All right, so I'm just drawing like a hypothetical boring graph, but what we're interested in is we're interested in the max or the min, and let's label that point with a B. So right at that peak is the B, or right at the bottom of the trough would be the B. So we find these B's by taking derivatives and setting them equal to 0, right? So now the question is, how do we know whether it's a max and a min? And so we create this table. So notice how we have a table over on the left here. And we're plugging X values, right? There's X values being listed, and we're plugging them into the derivative in this situation. And we use this information to classify it as a max, okay? And so that's what we're about to go through. I just wanted to sort of clarify what's going on in that on the left there. It's a table is what's happening here. And so what the first part is showing us, this part right here is showing us that at the point, oh, we got to label A, B, and C. So B is obviously the middle point, right? We have B labeled. A and C are going to be on either side of B. So there's A, there's C, there's A, there's C. So now that we have the graph set up, the idea is that B is in the middle, A and C are on the other side. And the first thing that we're being told is that the derivative at A is positive. And so that corresponds to this piece of the graph, right? So f prime of A is positive right here. And we know that because the function's increasing, right? So what this is really telling us, what this, come on, there we go. What this f prime of A positive telling us is that the function is increasing. Right, and we've learned this previously, right? Derivative tells us the slope of the tangent line. It tells us how the function's changing. And so if it's positive, we got an increasing graph. Then at B, it's 0, right? So at this middle point, it's 0. And so that means the function's flat. And flat is a relative term. It's only flat right at that instant. So that's right at the peak there, right? So that would be right here, right in the middle. And then the last part is telling us that the derivative is negative. Let's get a third color on that one, right? This part right here, this C, the derivative being negative there is telling us that the function is decreasing, right? So it corresponds to the right part of the graph. And we're not talking about any values here, right? We don't have any numbers for A, B, and C. I'm not talking about whether it's like positive 10 or positive 100. We're just saying positive means increasing, negative means decreasing. And so if we have that situation, then that is going to imply we have a max. Right? So based on the information, everything we just kind of determined here, all of this implies that we have a maximum at x equals b. All right, I'm going to pause there real quick and let everyone finish writing stuff down, see if there are questions. I'm going to just reiterate one more time. This is known as the first derivative test. And we'll obviously see a bunch of examples. This is the focus of the homework and just really the focus of the next couple of weeks, because then we'll start using this to find interesting critical points. Anything that I can clarify before I just sort of clarify the whole process again? Okay, so we take derivatives to find b, right? So this b right here is found with the derivative. And the question is it a max or a min? We plug points in on either side of that. So we just pick a point to the left, pick a point to the right. If it's positive, that means increasing. Flat means it, or sorry, 0 means it flattens out. And then negative means it's decreasing. And so that implies we have a maximum. And you can probably imagine how we're going to figure out the min based on this too then, right? Okay, questions before we just finish, do that part? Maybe I'll do this one a little bit less detailed. Okay, so the first part then, instead of increasing, flat, decreasing, we have the opposite, right? Negative means decreasing. 0 means it's flat. And again, we're talking about the derivative. It's really important that sometimes I just lose track of that because it's clear to me. And where the derivative is negative, that means the rate of change, right? The derivative is 0. That means it's flat. The derivative is positive. That means it's increasing. And so putting that together in the picture describes what's going on in the picture to the right. Right? This first piece right here is negative. Right here, the derivative is 0. And right here, the derivative is positive. And so decreasing, flat, increasing is got to be a min. So based on this sort of exploration, we would conclude that we have a min at x equals b. So we look at the derivative to tell us information about the function. Keep that in mind too. The pictures on the right are the function, and we're using the derivative to sort of explore the function shape. Thoughts about any of that? Seems okay? Okay. So the bottom part, there's a third thing that we haven't explored, and that's the inflection point, right? So in this thing down here, we're going to look at inflection points, which again we're going to define once we talk about what concavity means. But anyway, inflection points. Let's look at this one. So there's two things going on. There's this thing on the right, or on the left, I should say. I'll do that in blue. In blue, notice what's happening. The derivative is negative, then 0, then negative again. And so this is implying we have decreasing. Let me zoom in a little bit so I can write a little bit easier. So the blue thing I've highlighted here implies that we're decreasing, then flat, then decreasing again. Right, so that's different. That's not going to be a max or a min. And similarly, something happens on the other side. Let me highlight the other side. If we have positive, 0, positive, so the purple stuff, that's the opposite, right? That's increasing, then flat, then increase again. So those don't make maxes or mins. That makes the inflection point that if you kind of, I'm pointing up because I'm pointing at the graph. If you look at the graphs that we looked at the start of class, it looks like this kind of thing, right? So the purple part, let's label our B again. So B is right in the middle. Increase, flat, then increase again would be like this. Increasing, flatten out, and then increase again. Right? And then with blue, we would do the decrease one. So if we're talking about ABC again, decrease, flat, decrease would be decreasing, but flatten out, but then decrease again. And so that would look like that. Right? So we have flat points in those middle spots, but these are what's known as points of inflection. And I hate to keep saying it, but I'll say it one more time. We'll define that more specifically in 2 pages. But it's important to just bring it up now because it's a flat point. And so you're going to find those points if you're solving the derivative equal to 0. So they're going to come up in the critical point process, but they're not maxes or mins. Right? They're the change in concavity is what we'll see. All right. Any clarifications there before we look at a couple examples? Do at least a couple and then ask you to probably look at one. Seems okay. All right. So there's 3 on the next page. I'll do 2 of them and then maybe ask you to think about one. Maybe split you up. Let me page ahead and remind myself what's coming up here. Then we've got concavity. Okay, great. So clarifications at all before we jump in? Everyone got this stuff written down? I can go to the next page. I don't need that. So much easier for in person, right? I can just see like, are people writing? I can't, so hard. Anyway, let me know if you want, if you need something. So we're going to find the critical points and we're going to classify them, right? So finding the critical points, just to kind of clarify, we're going to set the derivative equal to 0 and look for discontinuities. That's the definition of a critical point. And then we'll classify them using the first derivative test that we just sort of talked about a second ago. All right, so the derivative's super easy on this one. And they're all easy on this page because they're just power rules, right? Eventually, we're going to start doing the stuff with more complicated functions. We're going to start with some easy ones to ease us in. All right, anyway, the derivative here, easy power rule, right? Just 8x plus 6. And let's just go ahead and get the discontinuities out of the way. We've got polynomials, so they don't have discontinuities. We learned that in the continuity section, right? Polynomials are continuous everywhere. And so we don't have discontinuities. Let's just make that note. So y and y prime are polynomials. Therefore, no discontinuities. So we don't have to worry about discontinuities. And again, we're not going to worry about those until we sort of get our feet under us with respect to this stuff. We're just going to look at some polynomials, which is again, it's kind of the important part, right? That's the calculus part of this. Okay, so we find the critical points by setting the derivative equal to 0. So y prime equals 0. It's a nice, easy linear function, so it's easy to solve. Just subtract 6, divide by 8, and we get critical points. And there's only one of them, I guess, so it's a critical point. And it's going to be x equals minus 6/8 or minus 3/4. So we only have one critical point to worry about.
How did you get that point?
Just took the derivative here and set it equal to 0, right? So subtract 6, divide by 8.
Okay, yeah.
We'll get that one. Other questions? Okay, so this is a flat point. All we know is that at minus 6/8 or minus 3/4, it's flat. It could be the top of a hill. It could be the bottom of a trough. It could be one of those intermediate point of inflection things. And so we just pick a couple points around that point and plug them into the derivative. So let's do that. Let me pick another color here. I'm going to make my table just like on the last page, and we're going to plug them into the derivative. Super easy to do on this one because, again, it's just polynomial. And so the point we found was minus 3/4, right? And we know when we plug that into the derivative, we're going to get 0. And so the idea is what happens before that or after that. So before that, so to the left of that would be like -1, for example. So we'll test -1. And then after that would be 0. So we'll test 0, right? It's always good to pick things that are easy to plug in. So I just picked those, again, I'm picking those 2 points because I'm just trying to go on either side of that value. And again, we plug it into the derivative. And so when you plug -1 into that, you get -8 plus 6, which is negative. Doesn't really matter what the value is. The point is it's negative. And so that means the function is decreasing at that point. When you plug 3/4 in, when you plug that middle point in, you get 0. That's how we found it, right? We took the derivative and we set it equal to 0. So it shouldn't be surprising that when you plug it back in, you get -6 plus 6. Right? We already knew that. We already knew it was going to be flat there, but I don't know, maybe it's good to verify that. And then when you plug 0 in to the derivative, you get a positive number. So you've got an increasing situation. And so we have a min. I'm going to sort of lay it out a little more carefully. I'm going to draw a little picture here. But that's the min. Trying to decide if I want to graph it quick. Do we have enough time to do that? What would be nice if I could figure out a way to like freeze this up here so people could keep writing. Then I could go do something else on my iPad. I wonder if there's a way to do that. I think I could. I think you can do that some way, but I don't know how. Anyway, can I clarify something? Someone say something? I guess I could just graph it on my computer, then just draw it there. That might be an easy thing to do. I think it just looks like an x squared thing, but let's just be sure. I'm looking at my computer. Yes, of course. All right, no questions? So this is what the graph looks like if we were going to graph this thing. I'll just leave the y-axis off. At -3/4, it looks like a min. It just kind of comes down and does this. And we know that because we plugged something in at -1 and 0 on either side of it, right? And right, this piece told us this. This piece just told us it's flat right there. And then this piece told us the right side. Now you want to pick points kind of close to it, right? Now, if there's only one critical point, it doesn't matter. But if you've got a bunch of them, you don't want to skip over one by picking something too far away. So pick something easy to plug in. -1 and 0 are easy, but not way far away from it. Can I clarify anything there? Let me, I guess, write down the take home. The final take home is we have a min. We have proved we have a min using the first derivative test. So x equals -3/4 is a min. Oh, yes. Let me actually clarify. Is this a global min or a local min? Let me actually rewrite the whole thing. Thoughts about that? Global or local min?
Global.
It's a global min. There's only one, right? If we found a bunch of them, we'd have to think about which is the smallest. There's only one, so it's got to be the smallest. And so that's a takeaway. But sometimes people get confused about the difference between there's a min there and what is the min. To find what the value of the minimum is, you take that x value and you plug it into the original. Okay, let me zoom in on that because I'm gonna have to write a little smaller here. To find the min, to find what the actual minimum value is, because that's what's most important, right? If this was, remember, some population thing we care about or whatever, this is a population of animals. We want to know what the smallest value of that is. It's at -3/4, but to find what the minimum is, you plug it into the function. To find the minimum value, you plug -3/4 into the original. In this case, y. Oops, not original. So if you want to know what the actual minimum value is, you plug it into the original. So the original was 4x² plus 6x. So 4 times 3/4 squared plus -3/4, excuse me, plus 6 times -3/4 would tell you the minimum value. And that is approximately -2¼ So it's important just to realize the difference between those two things, because homework will ask you those things. It might say, where is the minimum? And you'd say, oh, it's x at x -3/4. If the question is, what is the minimum value? You need to take that and find the minimum by plugging it in. Can I clarify that? That's an important point. That's like an important clarification thing, because you could do everything right, but if you don't just take that next step, you could be like getting the wrong answer in web work or something like that.
So I have a question.
Yeah, go ahead, Tommy.
I'll go first. Cool. So if you ask where the min is, it's the x value, right?
Correct.
And then what is it? You plug it into the original, and then you get the y, which is what the min is.
That's right. Yeah. So that's exactly right. Yeah. Someone else want to say something?
Yeah. I was wondering if there was a way to find the local min.
So a global min is also a local min. Local just means that it's the bottom of a trough or the top of a peak. Global just means it's the biggest one. And so this global one is also a local one. Does that make sense? Just kind of looking at the picture, or even back to the definition. The local part just means that it's the biggest or the smallest nearby. And the global thing just means the biggest overall. And so I'll just say that one more time. Global mins are also local. Local mins are not necessarily global, if that makes sense. Yeah, thanks for those questions. Other things about this one? Let me slide back here. Other questions about this particular one?
Yeah, I'm just trying to relate the table where you have -1 for x, and then looking at the graph, -1. The left is decreasing, the right's increasing, but like, I don't know, it's just kind of.
So these are the derivative values here, right?
Yeah.
So it's not, you're plugging things into you're determining the rate of change. So this is telling us the rate of change at those values, not the function value, but it's telling us just, is the tangent line pointing down, or is the tangent line pointing up, or is it flat? And so the tangent line pointing down, let me make this a little more clear, right? So this negative thing implies that the tangent line right here has a negative slope.
Oh, okay, and then if the x value is 0, the slope is 6.
So at the middle point, like, let me do it in another color. This one being flat just means that this tangent line is horizontal.
Mm-hmm.
Right? The slope is 0 on horizontal lines. And then the positive part is just telling us that the tangent line at 0 has got a positive slope.
Of 6?
Of 6, yeah.
Okay, and the -1.
So the specific value is, I was trying to say that these values are not super important.
Yeah, I was just trying to like connect the graph and the table.
Yes. So the specific value is not important, but what you could say is this is at -2. I'm sorry, -1. The graph is decreasing at a less steep rate than at 0 because 6 is bigger than -2. Right. So all we're really learning from this is decreasing, flat, increasing. And it sounds like maybe in your mind you're taking a step further and thinking like, oh, well, not only is it decreasing or increasing, but the rate at which it's increasing or decreasing.
Yeah. All right. I got it though.
And I see Rashid saying, if you were to plug -2, 0, and 6 into the original, you would find the y parts. That's right. Yeah. So let me clear up this graph a little bit. So if you wanted to know, when you plug this in, if you want to know this specific value on the graph, you plug it into the original. Correct. Just like we found that when you plug -3/4 in, you get -2.25. Yes, that's right. All right, keep them coming. This is good. It means you're thinking about this stuff, wondering how it relates. Anything else there? All right. So this one is sort of like the easiest possible situation because we've got a polynomial, so the derivative wasn't hard. It only had one min, which meant solving the equation was easy, and we only had to like plug things into one thing, right? So they certainly become more involved, is all I'm trying to say, not to like scare anyone, but like the next one, we'll see all of a sudden, I'm going to skip the middle one and let you think about that one. I'm going to do this one because this one has a t cubed, and every time you add a new power, it basically adds a new curve. Most of the time it adds a curve in the graph, which usually adds a critical point. And so just be aware of that. As the bigger the powers go up, the more critical points there end up being. So anyway, let me just do this one. It's not terrible, but there's going to be more than one. There's going to be two. And so again, we just take the derivative. It's an easy power rule. 3t squared plus 2t minus 1. No problem. Again, we just got a polynomial, so there's no discontinuities. It is worth saying that because eventually we're going to have to start thinking about that. And I don't want it all of a sudden to be like, oh, well, you never mentioned that before. So I'm going to keep writing this down until we actually start doing it. But anyway, h and h prime are both polynomials. And so we don't have to worry about discontinuities. Again, just write that down so that later when there is one, you see that and you're like, oh yeah, I do have to think about that. I have to think about that quick. Like just kind of looking ahead, we won't see one for a little bit, but like once there starts being fractions, for example, right? This is going to have potentially discontinuities. Maybe, maybe not on that one actually. But anyway. Okay. So we've got the derivative, no discontinuities. We're just going to be looking at maxes and mins and potentially points of inflection. So we take the derivative and we set it equal to 0. It's going to be a very common process that we're going to be doing quite a bit. And it's a quadratic. And so we can either factor it or, let me set it equal to 0, or use a quadratic formula, right? Those things will both work. This one's factorable. And so you can either 1 factor or 2 use the quadratic formula. On tests and stuff like that, I usually put things on there that are factorable, right? Just to speed things up and not really put the pressure on too much. But in homework and definitely applications, quadratic formula is just nice because it always works, right? You don't have to worry too much about that. So I'm going to factor this one, but just be aware that if there's a harder problem, you might want to use the quadratic formula. This one factors into 3t minus 1, t plus 1. And we're multiplying two things there, right? We're multiplying those two factors, 3t minus 1. We're multiplying that by t plus 1, and we want that to be 0. The only way you can multiply two things and get 0 is if one of them is 0 themselves. And so that's why you take them separately and set them equal to 0. All right, people now, oftentimes, I feel like you've definitely seen that before, right? High school, even middle school, probably. But oftentimes people lose track of why we do that. We're trying to multiply two things and get 0. The only way you can do that is if one of those two things is 0. And so we just set those equal to 0. solve for t, and we get 2 critical points in this case. So these are our 2 critical points. Is it okay? You guys know what I mean when I say the quadratic formula? Is that all right? Some of you guys heard me sing the song in pre-calc. It's a mnemonic device. I won't sing it here, but if you look up some of my other videos, you can hear me singing. Some of my pre-calc videos.
Yeah, I was gonna sing it.
Yeah, sing it, Josh. Let's hear it.
I was hoping you would.
Oh, no, I thought you were trying to volunteer. I will not be singing today. Gosh, you guys can bring in note cards and stuff too. You don't even need to sing it anymore, probably. I was really shocked that someone was volunteering to sing that, so I guess that makes sense. Okay, no questions though. Seems okay so far. So these are flat points, right? Just to be clear, critical points. These are the flat ones. And the questions is, are they maxes? Are they mins? Are they points of inflection? So we're just going to test a few points. And it's important to kind of think about, now that we have more than one, what points do we test? We just found these 2 critical points. And so when we're thinking about places to choose, we need to pick something in each one of the spots, right? And so we want to test points here, here, and here. In other words, that middle point can be used to tell you something about both tables. So that's one helpful thing. And the thing I was also mentioning is make sure that you pick something between -1 and 1/3, for example. And so 0 is a good spot there. All right, does that seem okay? I'm going to draw the tables out. And so we will test those points in the following table. Tables. We need 2 tables because we have 2 critical points. And one of them is going to test -1. The other one is going to test 1/3. Okay, I'm just going to sort of set the tables up. And then we want to pick a number to the left of -1. So -2 is good there. We want to pick a number to the right of 0, -1, excuse me. So 0 is good there. And just to be clear, right, this is going to be the same spot that goes right here. And so you don't need to test that twice. Just trying to save some time. And then the third point, bigger than 1/3, is just 1, right? So we're picking easy numbers, best numbers we can. And we're just plugging them into the derivative. Just going to pause there, and it'd be helpful if everyone kind of looked at something as I said something, I think. So I just want to make sure everyone's finished writing. And I'm happy to clarify something. Let's see. So a couple of questions in the chat. When you took the derivative, the 1 became -1 instead of 0. Oh, so the 1, let me zoom in on that. This, oops, that became the 1. Right? This became this. The 1 just goes to 0 when you take the derivative. Let me know if they can clarify that, Sebastian. All right, -t becomes -1. Okay, good. And then the other question I see there says, oh, Roger was answering that. Sorry. Thanks, Roger. Should read both questions before I go. Other thoughts? Seems okay. Oh, so I was going to say, you need to plug these points in. We're plugging these points into the derivative. And so what I was going to point out, and it'd be helpful to look at this, you can use this version if you want, but then you have to square something, which is okay. But I'm just pointing out that you could also just use the factored version. And all we really care about is whether the outcome is positive or negative, right? The specific value is not currently important. And so sometimes plugging it into the factored form is easier to figure it out because you just say like, oh, is this piece positive or negative? Is this piece positive or negative? When you multiply them, do you get positive or negative? And so it's like a quicker way to plug things in sometimes. So anyway, I just want to mention that. I'll just kind of write the details out in the first one. Oops. So when you plug in -2 into the first piece, you might get like 3 times -2 minus 1 times t, oops, -2 plus 1, right? That's the kind of thing. It's kind of easier to do it in the factored form because then it's like, oh, I have -7 and I'm multiplying it by -1. So you have two negatives, multiply them, you get a positive, right? You get +7. So I'm just going to write the details out in this first one in case people are still confused about what's going on there. So I'm going to plug it into, I'm using this piece right here to do that, right? So when you plug in -1, it looks like this then. You'll have 3 times -1 minus 1 minus 1 plus 1. And obviously we get 0. Slide this over. And then the third piece, 3 times 0 minus 1 times 0 plus 1. So you're going to get -1 times 1, which is -1. So increasing, flat, decreasing. Increasing, flat, decreasing would be a max. So, all right. I'm just going to fill in the other table. I won't write out the details too much. So what I was trying to point out before, though, too, is we don't have to do this one again, right? This one that we just did is going to be the same answer in the first spot. So you don't have to plug it in a second time. It's not like it's hard to do in this case, but sometimes it might be difficult. So just know that so you get the same thing, right? So we get -1 again, which is decreasing. When you plug in 1/3, you get 0. And when you plug in 1, you get 4. And so decreasing, flat, increasing. Can I zoom in there and do that? So this one is decreasing, flat, increasing. So that's a min. And if we want to know what the minimum or maximum is, just to reiterate that again, you plug it into the original function. So the max is at -1. Oh, these are t values too. I wrote x. There should be t's. I'm sorry. Doesn't really matter here, but just to be consistent and correct. If you want to know the max, plug it in. So you would plug that into the original, and you would get, in this case, 2. Or if you want to know what the min is, plug that in. Okie dokie. Pause there and see how that looks. Just going to pull the homework up too and remind myself some of the stuff in there. The stuff in the homework is going to be trickier than this. And so we're introducing the concept, letting you look at some of the homework. Maybe on Wednesday we can dig into some of the homework too. Pull some up here. That's just some questions about this first example though. All right. What do you think about the second one here, this middle one? So I skipped over this one because it's only going to end up having one critical point, if I'm not mistaken. Is that right? Yeah. So just in the interest of time, instead of doing this in breakout rooms, let's just think about this together. And I'm going to kind of do it in stages here and ask you to think about each step. So let's take the derivative together, set it equal to 0. All right, this one's not too hard. When you take the derivative again, nice easy power rule, just 3y squared. We still don't have any discontinuities. In fact, I'm going to do the lazy thing and just copy this. I think I can do that, right? John showed me that last time, yeah. All right, we don't have any discontinuities. We just have polynomials. It's important we have that there so that we remember to do that later. All right, so we're just going to have regular old critical points, maxes or mins, or maybe point of inflection here. And we set the derivative equal to 0. How do we actually do that one? Sometimes people get confused about this. So if we take the derivative and set it equal to 0, that just looks like 3y squared equals 0. Do we get confused by that at all? What's that critical point? What would you have to plug into y in order to get a 0 there?
0.
Just 0 itself, right? The only time you can multiply or raise things to powers and get 0 if you have a 0. Just to be clear, sometimes people get confused. If you divided by 3, you'd get, you'd get y squared equals 0. If you took a square root, you'd get y equals plus or minus 0. And so just to be clear, you can sort of think about it using normal techniques as well. Anyway, only one critical point. So one critical point at y equals 0. I should clarify too, the y in this function is not the y value on the y-axis. It's just the input. Like if we graph this function, if we were going to graph this, we would have y down here, and then we have g of y on the x-axis, or on the vertical axis. I should remember to change that. I know that confuses people sometimes too. We're not thinking about y as being an output. We're thinking about it as an input here. Anyway, there's only one critical point. Is that okay? All right, classify it. Go ahead. I'm gonna give you a minute to think about that one. I'll set the table up and sort of set the stage or whatever. But you should be able to, I think, do this one pretty easy at this point. So our table, we're plugging things into the derivative. I wrote x instead of y though, of course. And we want to test around 0, and so just pick plus and minus 1, right? Those are the easiest numbers. So minus 1 to the left, plus 1 to the right. And just plug them right into the derivative, and the derivative is super easy. It's just 3y squared. So just plugging those things right in there, and we'll be able to have an understanding of what it looks like. Just going to pause there for 1 second, let folks just think about that briefly. We've seen a couple maxes and mins in the last couple examples, so it shouldn't be too surprising that we're going to end up with a point of inflection on this one. And we should be able to see that without really doing too much work because the derivative's got a square in it, right? So when you square negative numbers, it acts just like positive numbers. So when you plug in plus or minus 1 and square it, you get the same output, in other words. And so, I don't know, maybe that was long enough to do it, but when you plug in -1, you're going to get 3, which is a positive number. You get 0 in the middle. And when you plug in +1, you also get a positive number, right? So we have increasing, flattening out, and then increasing again. And so that looks like this, right? Increasing, flattening out, and then increasing. So we get that point of inflection. Very good. So this right here is a point of inflection. The reason I wanted to move on to the next thing here is because I'd like to learn about what a point of inflection is, just for continuity's sake today. Okay, thoughts about the first derivative test at all? Or how we get any of those things? You know, I know it involves some algebra, so sometimes people get a little scared because we're moving into calculus and doing derivatives and things with it, but then people get stuck back in some algebra stuff. So if you want to hear more about algebra, that's fine. Just know that it's going to be, we're going to need to know some algebra. So let me help you is what I'm trying to say. Anything clarify so far?
Can you go down to the third one? I just got something else.
Has anyone looked at the homework at all for this stuff? Just kind of curious if.
I did this morning. It looked pretty confusing.
Yeah, and it might be kind of confusing before this. I maybe would go back and see how it looks after today's class. And again, I would love to start out classes by looking at some homework and going through some of that stuff. So let me know Wednesday. Is next page concavity? Yeah. Okay. Anything else before we keep going? I'm just going to introduce concavity and probably end after that. Let's see. Someone wants to copy still here. All right, I'm gonna page on down. Is that okay? All right. So concavity, I usually just try to draw a couple pictures to explain concavity. And sometimes, just for future class reference, sometimes you hear people use the words convex versus concave. I don't know if anyone's familiar with those words. I don't like using those two contrasting words because sometimes it's confusing to remember which is which. And so instead, what I try to think about or use as words is just concave up and concave down. So if you're used to concave or convex, if you've heard this before, just know that I try to avoid that. And that's a pretty common thing, actually. People generally avoid that confusion by saying concave up and down. So anyway, concavity, I always think about a cave or something when I heard that word concavity, and that's kind of an apt description when you're thinking about what it means. So concave up, things that are graphs that are concave up, let me draw 3 graphs real quick, have a curvature that is upward facing. So an upward facing curve might look like this, for example, like x squared. But it doesn't have to be that drastic, right? So something like this, for example, is also concave up, or something like this with even slighter curvature is also concave up. And so when you hear the word concave up, you should just thinking it has upward facing curvature, like a bowl, right? Concave up. And so concave down, I'm sure you could imagine, is the same thing, but just downward facing. So we had a couple more graphs here. Let's do the same 3 graphs, just the opposite, right? So concave down then would be minus x squared, or something like this, or something like this. So it can be kind of slight, like the second 2, can be drastic, like the first one, but it's an upside down bowl, right? You wouldn't try to dump your cereal into concave down. Okay, and it turns out the second derivative tells us about that curvature. That's why we're talking about it here, and that's why we talked about sort of higher order derivatives. I mentioned this, I alluded to this last time a little bit, and I'm glad we're just sort of putting this together with the first derivative test. So I'm going to explain how the second derivative does that, but are there questions about what I'm trying to say? Excuse me, about concave up or down? Okay. So again, that's sort of the definition, but this is the explanation about why that makes sense, right? So we know, let me make this a little bit bigger. We know this, right? We know that when we do a derivative, it tells us the rate of change. I hope we know that by now. Slope of the tangent line. And so if we do the derivative of the derivative, which we talked about last time, right? Second derivative, higher order derivative. What we mentioned last time, it tells us how the rate of change is changing. And we had called that acceleration previously. But let's think about it in this other kind of context, right? So the second derivative is how the rate of change is changing. So let's draw another picture. And let's say that the second derivative is negative at some point, A. So here's A. Let's draw a graph. If the rate of change is decreasing, maybe I should slide this over and write something here. Right, so second derivative being negative means the rate of change, f prime, is decreasing. In other words, the tangent lines are getting flatter. Maybe that's a better way to say it. Let me do that another color, i.e. tangent lines are getting flatter. If we have a graph where the tangent lines are getting flatter at a point over a certain interval, that means they used to be certain steepness and then they're less steep. And so that might look like this. Right, just kind of thinking about the tangent lines. Like the tangent line right here would be a certain steepness, but then a little bit after it would be less steep, right? The tangent lines are flattening out. The derivative's getting less intense. In other words, we end up with this downwards facing curvature is what I'm trying to point. Right, we've got concave down. i.e. second derivative is negative. I'm just trying to like rationalize through why that second derivative gives us that curvature, because the slope of the tangent line is flattening out. And then the opposite's true if we have, I'll kind of do this a little bit quicker. If we have the second derivative being positive, the tangent line's getting more steep. And so that's going to do the opposite thing then, right? If the tangent line gets more steep at a point, it's going to end up doing a concave up thing, because we'll have like not a very steep tangent line and then a steeper tangent line, and that's going to make a bowl shape. Okay. So this will tell us concave down. Oops. Positive. Okay. And so it's summarized below, but I would like to just see if there's, I know I say this a lot, but it's always just better in math if we understand why something's the case. If we just sort of make sense to us in our brain why the second derivative tells us concave down, because it's informing us about the first derivative, and we know what the first derivative means, like if that all just makes sense, you don't need to memorize anything, right? When the test comes around, you just show me that thing that you learned, and it makes sense. And it's fine to have to memorize things and have to study. I'm just trying to help you avoid some studying if you can. Anyway, I've rambled. Other questions? Anyone developed a question yet? Seems all right. Okay, and so this thing is being told by the first part. The second thing is being told by the second part. And so the third thing there is what we haven't explored, which is what a point of inflection is. And so that third thing is telling us what a point of inflection is. And so let's hone in on this red outline part real quick. So the red outline part tells us if the second derivative is 0, that means we have no concavity, right? If the second derivative tells us concavity, second derivative being 0 means no concavity. No concavity is almost, mathematicians love coming up with special cases of things where they don't fit the definition. But in our purposes, in our sort of basic introduction to calculus class, second derivative being 0 is going to mean a point of inflection. And as it says right here, a point of inflection is where the graph switches concavity. So let's just go back up to that first picture that we looked at the start of class that we mentioned last time, right? If we look at this point of inflection, before that, it's concave down, and after it, it's concave up, right? Maybe we can add those words to this picture, right? On this piece, oops, I meant to do that in pen. On this piece, we have concave up. Hopefully you can see that now, right? And on the piece before it, we have concave down. And at the point of inflection, it's switching those two things, right? It's switching from being downward bowl-shaped to upward bowl-shaped. And so the point of inflection is going to be where the second derivative is 0. So now we hopefully have a good understanding of everything on this graph. And I would like to add a few words to this definition as well. All right, so let me add a couple notes on this page here. So here's what a point of inflection is. Maybe we can add a little box. I'm going to write a few things in here. So let's draw a couple point of inflections. So point of inflection could be like this, or like this. These are the ones that are on the first page. But it doesn't have to be like that. And the reason I want to draw a second one is because sometimes point of inflections can look like something like this, for example. Right? Do you agree that this right here is a point of inflection? Because right before that point, and let me zoom in on this picture, right before the blue A, it's definitely downward curved, right? And right after the blue A, it's definitely upward curved. And so it's a point of inflection in the middle. The difference is in the first derivative at those points, is what I'm trying to point out here. So let me just sort of let everyone write that down, and then I think it's important again if everyone's sort of watching for this last part. The questions about how each of those three graphs that are on the page right now, how those are points of inflection. We've changed the curvature at those points. The thing that I think is important to note is that on the places on the left, the first derivative is 0 because it's flat, and the second derivative is 0 because it's an inflection point. So both the derivatives are 0 on the left. On the right, the first derivative is not 0, it's negative because the function is decreasing there. So that's actually not going to come out of, it's not a critical point. But the second derivative will be 0 because it's an inflection point. You see that? And we'll explore these in some examples and things. But what I'm trying to point out is points of inflection are not always going to be critical points because they're not always going to be situations where it's a flat point, like on the blue graph on the right. Thoughts about that? See what I'm trying to say there? And so just in the last minute, actually, let me let people finish writing this down, and I'm going to graph something real quick and then illustrate. I'm going to graph this picture at the bottom here so I can draw the picture, and then we will end on this example. I just want to draw the picture real quick. Good. Okay, that's what I thought it looked like. Questions about this, what I've written here? Kind of questions about concavity or what I'm saying there? Just kind of highlight the point here with this the last example. Anything in the chat? Okay. So just real quick then, let's just draw this picture. And I just did it on my computer. And when I draw this graph, it looks like this. Let me make sure that's right, actually. Yeah. Kind of does this kind of thing. That's what this g of x function looks like. And so it has a max and a min, just looking at the picture, right? There's a max on the left side, there's a min on the right side, and there's got to be a point of inflection between them because we got concave down switching to concave up. And so just, we're not going to do a full analysis here, but I just want to point out to kind of illustrate, first of all, that this graph here is kind of like the right-hand graph. It looks actually very similar to that graph, right? And so notice how if we take the derivative of this thing, which again is a nice easy power rule, if we set that equal to 0, we get 2 critical points, and that's going to be the max and the min. Question, John? Anyone? Okay. And so I'm not going to do it, but you can prove that these are the maxes and min using the first derivative test that we just did. And you can just look at the graph to be convinced. Right? If you don't believe me, you can graph it, but this is the minus square root of 1/3, and then the plus 1 is on the other side. But notice how the point of inflection did not come up on this analysis. That's sort of the takeaway I'm trying to say is that sometimes they come up on the critical points, like this example in the middle from the last time, right? When we did this one a second ago, we ended up finding the point of inflection because it happened to be one of those flat points of inflection. But on this one, it's not a flat point of inflection in the middle, and so it doesn't come up as a critical point. If we want to actually find the inflection point, we need to take a second derivative and set that equal to 0. And so that's all I'm trying to point out here is to find the point of inflection. You can set the second derivative equal to 0. And so if we take the second derivative, it's a g though, not an f. Second derivative is 6x, set that equal to 0. We find that x equals 0 is the point of inflection. And again, you can see that on the graph, right? Right where it crosses the y-axis is where it kind of switches concavity. So x equals 0 is the point of inflection. And again, just look at the picture and hopefully you agree with that. So we will explore this a little bit more. We also have something called the second derivative test to show us maxes and mins. So we'll see that as well. I'm going to stop here though, see if there are any questions. I'm happy to look at homework if you got it in the last couple of minutes, whatever would be helpful for you. But that's all I've got. Thanks. Questions? Can I clarify something? Homework questions? Anything there? You're welcome to take off if not. I will stick around to see if